Hi everyone, my name is Shir and I'm going to present Tame the While with Byzantine Linearizability, reliable podcast, snapshots and asset transfer. This is a joint work with my advisor Edith Kedar from the Technion. So let's start by covering the outline of this talk. So I'm going to start with describing the problem we are trying to solve here and give some motivation to it. Then we'll define a new correctness conditions called Byzantine Linearizability. And then we will use this notion to present both lower and upper bounds on many useful objects. Finally, we'll summarize. So let's start. So probably most of you heard about Bitcoin. If not, this is probably the wrong conference for you. But Bitcoin was created to implement asset transfer. And of course, it didn't stop there, and many other cryptocurrencies followed the same idea. And they all implemented the same idea of asset transfer. So what is an asset transfer object? An asset transfer has two operations, transfer and balance. In a transfer operation, account source can move amount of his coins, let's say, to a destination if he has enough money. If not, the operation fails. The other operation, balance, simply returns the balance of some account. And the way all of these cryptocurrencies work is that they all implement state machine replication, and specifically, they all rely on consensus to do so. But 2 years ago, Garai et al. Has the very cool result, and they showed that this is unnecessary, meaning asset transfer can be solved without consensus. Even in the asynchronous systems where we know consensus cannot be solved, asset transfer can be implemented. They presented construction using reliable single-item registers, which I'll mark here at the blue Lego piece, that can be used by non-Byzantine client processes. And in their implementation, every process needs to write only to its own registry. So why do we need this Lego piece? Lego pieces allow us to construct more complex, more useful objects. So luckily, such register can be constructed, and even efficiently, in a distributed asynchronous systems, even if we have Byzantine server processes. Not so luckily, on the other hand, the blockchain world does not assume that everyone behaves as they should, right? They do assume Byzantine clients that try to make bigger revenues and may not be ethical while doing so. So when we want to use such registers in the presence of Byzantine clients, we need to be a bit more careful. So in this work, we ask ourselves the following questions. Let's assume we do have efficient, reliable single-writer registers in an asynchronous systems where we know consensus is impossible. We want to know what can be done and what cannot be done when such registers are being used by Byzantine clients. And the model we assume is the shared memory model, and we assume it is reliable because we know there exists such a construction for the registers and Byzantine client processes. So let's start by examining only registers and see what happens to them when being used by Byzantine clients. So first of all, multi-writer registers. So if you think about it, multi-writer registers are completely meaningless. And why that? They can prevent any kind of communication between correct processes. Whenever a correct process comes to read some value, another Byzantine client, when we know also the adversary control the schedule, can embed a write with whatever value wants just before the correct read. What about single writer registers? So for the Byzantine registers, this is the same case. But we do have now some registers that belong to correct processes from which the correct processes can communicate. But we want to know what they can do, what kind of information can they transfer to each other. So more specifically, we have the following questions. First of all, what useful objects can be constructed using registers? For example, we talked about asset transfer. Can we construct asset transfer and implement the next cool blockchain? 2, how can processes collaborate to obtain a state of the whole system? So this relates both to Snapshot and asset transfer, right? If I want to know the balance of different accounts, not only my account. And even if I'm talking about my account, how do I know if someone did transfer or not, if he just deleted it? We'll see such examples in the following slides. And how can we make sure that Byzantine don't equivocate if they can do whatever they want with their register? In particular, we want to close the gap on the following table. So we know that in the crash failure, this is the result or the resilience required for implementing reliable broadcast, snapshot, and asset transfer. And we know the answers for the crash failure case. We know that in the message passing is 2f+1, and in shared memory, it's f+1. Okay, we can be more resilient in the shared memory model. So now for the Byzantine case, we know for a message passing that the result is 3f+1. But the question is it the same result for the shared memory? And if not, we suspect that we can lower the resilience as well, or improve the resilience. So let's start with a straightforward attempt to implement asset transfer using single writer registers. So we have 5 processes over here, and each of them have an initial balance written below the characters. And let's say that D now wants to transfer its 10 coins to A. So what he can do, he can write transfer from D to A amount of 10 in its own registers. Then what we would expect to happen is that the balance of A is increased by 10 and the balance of D is decreased by 10. But you can see that D is not so calm. Okay, he's more than that, he's Byzantine. And therefore he can just delete whatever he wrote in its registers before that. So on one hand, the transfer did complete, but then any evidence of that was removed from the system. So what happens is D basically redeemed himself his money back. So now we have A with 15 coins, but D also have his 10 coins. Now we can use the same 10 coins to transfer them to B. Okay, so then again, he writes the transfer, B receives 10 coins, and D loses it. So this naive implementation is, it doesn't work, as you probably could anticipate. Okay, we simply created the double spend here, which of course is something we want to avoid in an asset transfer. So this doesn't work. We know that Snapshot could have solved it. Okay, this is the same idea as the consensus number of cryptocurrencies that I mentioned before. Okay, if we had a snapshot, then everything would be great. We have implementation. Unfortunately, the construction for snapshot we all know of doesn't carry on when used by Byzantine clients. Okay, so for example, A updated this yellow dream in its cell, and now someone wants to take a snapshot. So how do they normally do that? They do a double collect. Okay, so everyone tried to agree on 2 consecutive collects of the array without any changes in between. Okay, and they help each other, and we want them to be able to read the same thing twice. Unfortunately, in the presence of Byzantine clients, this may never happen, right? Because let's say Joy here comes and she reads the red circle, and the moment she comes back for the second try, or someone else comes for another try, maybe trying to help her, the Byzantine can simply remove this. Okay, so someone may never have a double collect, a successful double collect. So is it even possible to create meaningful objects? Okay, so maybe let's start by defining what meaningful even means. So to do this, we define a new correctness conditions called Byzantine Linearizability. So the goal of Byzantine Linearizability is to prevent Byzantine processes from changing their mind, just like they did. What we want to do is to take each Byzantine operation and decide whether this operation took place or not. Was the first transfer operation successful and it is fixed for the rest of the time, or can D regrets it? So we don't want him to be able to regret his actions. But the problem is that Byzantine don't necessarily use API operations, right? D may never call the transfer because he just wrote and deleted stuff from his registers. So can we still do that? So the answer is yes, and let's see how we do it. So Byzantine linearizability is defined with respect to a set of correct processes. So in this case, which represent what we saw before, we have A and B, they are the correct processes, and D is Byzantine. And what we do is we look at the execution. So balance A and balance B is operations that were invoked by correct processes. The transfers, as I said, D may never use the API, but this is what we expect him to do. So this kind of makes sense. And what we do is we start by looking only at correct operations. Okay, so we ignore whatever the Byzantine did or did not do. And now we ask ourselves, is it possible to add Byzantine operation to this history such that the whole run makes sense, such that the whole run is linearizable as we know linearizability? So if you remember before, we had the transfer and he could regret it. So in this case, let's see, if we want to add the transfer at the beginning of the execution by D, we must add it so the balance here is correct. The balance by A is correct. But if we did add this operation, then we couldn't add another between the two balances. So this execution is not Byzantine linearizable. What about this execution? Can we add Byzantine operation here? So in this case, yes, this execution is Byzantine linearizable because we can add the first transfer and it doesn't conflict with anything in the future. So this is good. Formally, Byzantine linearizability is the following. We say that the history H is Byzantine linearizable if there exists an history H prime such that correct operations in H and H prime are the same, and H prime is linearizable. Okay, so this is H prime is exactly the execution, the history we were trying to create. We took the correct processes and tried to make it make sense. And if you think about it for a moment, multi-writer registers and single-writer registers are trivially Byzantine linearizable. And this is just as we mentioned before. If I have any of these registers, whenever a correct process reads something, I can add a Byzantine write just immediately before that. And the main result of this paper is the following. There exists F-resilient Byzantine linearizable implementation of reliable broadcasts, snapshot, and asset transfer objects with N processes if and only if F is less than half of the problem of the processes. So let's mention our lower bound. So as you expect, the lower bound is just one side of the if and only if. And it says that for any F greater than 2, there does not exist F-resilient Byzantine linearizable implementation of the discussed objects using only single-writer multi-reader registers. And the way we prove it is we prove it directly for asset transfer. So what we do is we start with an execution where with some processes, only one coin in the system, and in some magic way, we create another one pop-up in there. Okay, and we use this indistinguishability arguments to do so. Then, because asset transfer has implementation from both reliable broadcast and from snapshot, we can conclude the same result for them as well. So now we can extend the model, and we can now add that n equals to 2f plus 1, and that correct processes take infinitely many steps in the execution. This is another conclusions from our lower bound. So now let's present our upper bounds, and we'll start with the reliable broadcast object. So you all know reliable broadcast as a message passing primitive where I can reliable broadcast a message and processes will receive it. Maybe they echo some of this information, but the information comes to them. And in the shared memory model, we define it a bit different. We define it in a push fashion. So to broadcast a message, you invoke a broadcast operation with the message M. But in order to deliver a message, you need to actively invoke this operation, this deliver operation with the arguments of the process from which you are trying to deliver a message and a timestamp. And to implement them, we are using a helper function called refresh. And for simplicity, I will ignore the timestamp for now. So let's view it by example. So what are the variables we're using? So in this system, we have 2f plus 1, f is 1, we have Shir, Edith, and Zeus, and each of the participants have 4 registers: send, echo, ready, and deliver. And in order to deliver a message from process P, for example, Edith tries to deliver a message from Edith herself, it can be delivered if P's message appears in some deliver register, it doesn't matter who, with f plus 1 ready signatures. So in this case, there is the message with 2 signatures by Shir and by Zeus. So Edith can deliver the message. Okay, the message is delivered. For the broadcast operation, first, so now Edith tries to broadcast this letter. First, it needs to write it in the send registers along with the signatures. But now every participant that broadcasts a message need to wait to be able to deliver it himself. Okay, so now Edith wrote it in the send register, but she cannot return until the message is delivered. So how do messages get delivered? How do we move from, how are we able to finish this broadcast operation? So here comes the refresh procedure. So processes call the refresh procedure infinitely often during the execution. In the model, we discussed it. So this is the refresh. At the first step, whenever someone calls the refresh, so now Zeus is the one to do so, it looks at all the messages in the send registers and copy them to the echo register. Okay, so here we can see Zeus did that. Now, Zeus looks for conflicts. Are there any other messages signed by Edith in the echo? Meaning suggesting she is Byzantine. So in this case, no. So Zeus can safely copy it to the ready register. And it also adds its own signature to it. Finally, it looks again for conflicts in the echo. This is sort of a double collect. And if there are no conflicts and there are f plus 1 ready signatures, it can copy it to deliver. In this case, there is only one signature in the ready, so this message cannot be delivered, and Zeus can move on with this life. And this is okay, because if you remember, Edith is still sleeping, she still haven't managed to deliver the message, so the broadcast was not completed. So we don't anticipate that concurrent deliver will succeed. Now Shir is Byzantine. She sees the message and copy it to echo. Then she also edits to ready with matching signatures. It doesn't even need to check for conflicts, doesn't follow any protocol. Now she can see there are 2 signatures in the ready, and it can put it in the delivery, but as she is malicious, she removes any previous footprints. Okay, so the message in the deliver, but any previous steps are now being removed. Now Edith wakes up and she wants to complete the broadcast. And we want to see if she can do that. So let's assume that she can. Okay, so there is 2 f plus 1 ready signatures in some deliver. So as we defined deliver before, she can take it home and deliver the message. So she completes the broadcast. But now what she does, she's savage, and when Zeus tries to deliver the message, she removes it. Okay, and now Zeus cannot find any f plus 1 signatures, ready signatures on the message. So his deliver fails. This is problematic because we now know that the broadcast was completed and there is a future non-concurrent deliver operation that failed. So we know that those should be able to deliver at this point. So how we solve it? Before delivering a message and finishing whatever operation, we copy the delivered message with the f plus 1 signatures to my own deliver register. So in this case, Edith, before completing the broadcast, she saw the message here she copy it locally to her own deliver register, and then she can safely return. Now, when Zeus comes and delivers the message, it is guaranteed to find it in its deliver register. And if you wonder why there are two middle steps in the climbing ladder, then you will have to read the paper. Okay, so Zeus can copy it and deliver as well. And finally, the snapshot operation. So the Snapshot API is, as you all know it, there is an update with some value and a snapshot taking a consistent view of the system. And for simplicity, we assume there are no timestamps, and updates are increasing. So first of all, a simple function that will be used a lot, an update collect. So we have here three participants. Each of them have a local array of size n. So in this case, n is 3, called collect. So update collect is when I'm trying to update, my own collect array with a given array. And the way I do it is I take the maximum of each index. So in this case, only the second index will be affected. The update operation is very simple. It is the following. When I am trying to update some value, I'm starting by updating my collect with all of the other arrays in the system. And then I write v in my own collect in the matching index. So for example, the dog wants to update 2. So what it does update collect with its own register, which of course have no effect. Then it update collect with the fox array. It updates the one in the middle. And finally, the last array of the cat. Okay, so the 4 will change. Now it can update the 2 in the relevant index in the first one, and then the update is finished. Now the snapshot, which is a bit more complex. So in a very high level, at the beginning, we do the same. We start by updating our collect with all the other arrays in the system. Then I take a picture, a snapshot of my local collect, for which I'll try to compare every step in the algorithm. So in a loop, I'm doing the following. I'll call the snapshot aux operation, which I'll discuss in a minute, and obtain some array. If this array is greater or equal to C, the snapshot I took here, the snapshot of the array I took here, then I can safely return it. Otherwise, I continue to call the snapshot aux again and again. So for the snapshot aux attempt, so the attempt is growing. So all processes during the execution infinitely often call snapshot aux with increasing attempts number. And at the beginning, every process collects the update collect its own array and broadcast it to all other processes. Then whenever I receive a collect, I update my view accordingly. So in this example, the dog received this array from the cat and it updates the flow. Then in every round to follow, we broadcast who are the processes I heard from in the previous asynchronous rounds. Okay, so in this point, the dog heard from himself and from the cat, so he tells everyone, this is the set of processes I heard from, dog and cat. And it is guaranteed that after a bounded number of rounds, a set of F+1 processes stabilize with the same view. Okay, it is guaranteed that the set of processes will be the same. And then because we always take the maximum, they will all converge to the same supremum. Okay, so here we have the dog and the cat, they all finish with the same array. This array can be safely returned, and at some point it is guaranteed that it will be greater than C, my local view at the beginning of the snapshot operation. Let's summarize. So first of all, we completed this table, right? We know that from the lower bound and from the upper bound that the optimal resilience for Byzantine clients using reliable broadcast snapshot and asset transfer in the shared memory model is 2F+1. we formalized Byzantine linearizability. We proved the lower bound for these objects, and then suggested algorithm with the same optimal resilience, and implemented the useful asset transfer and the even more useful objects, the reliable broadcast and snapshots. Thank you for listening.